This is from, as I have the dwarf book. Example 8.5. Okay. It's looks like a long transfer function, frequency response, in which we replaced S by J omega, as you see. We have the following factors here. You have a constant gain K of equal to 5, okay, this one. The second one is 1 over J omega integrated. This is the third one. The fourth one is 0 at this one. So 1 plus 0.1 J omega. And the fifth one is the quadratic term. Let's say second order term with omega n equals 50. And the damping ratio, I think, is with zeta. This is 2 zeta, so zeta is 0.3. Okay. So we will plot them one by one. The first one is 20, in terms of decibels, 20 log 5 is 14 decibels, which will be there. The second one will be basically, it will be a straight line with a minus 20 dB per decade, intersecting, let's say, omega equals 1 at 0 dB. The third one is this one. It has two asymptotes. One starts at like this and then goes down like that, and the third one has a frequency at, this will be at omega equals 1 over 0.5, so omega equals 2, okay? And the fourth one again has two asymptotes. Here it will be like this one, because it's a zero, like here. And the omega equals 10 here. And the fifth one is, again, it has two asymptotes, but which is like this. And then this has a slope of -2, and the omega here is equal to 50, omega n. Okay, and the slope is -40 dB per. Okay. So if I copy and paste them from the book, it will be a better picture, I hope.
Hocam biraz yukarıya çekme şansınız var mı acaba?
Neyi?
Müsait olduğunuzda. Yazıyor hocam.
Ha, tabii pardon.
Çok teşekkürler.
I'm going to paste now what we have. So this is the picture of each of the individual terms, as you see. The first one is 14 dBs, straight line. The second one, by the way, this is a logarithmic plot in terms of omega. As you see, it is 0.1, 1, 10, 100. They are all equidistant. From 0.1 to 1 is equidistant with 1 to 10, from 10 to 100. So we have in the second one, we have a straight line with a slope of -20 dBs from 1 to 10, let's say, and passing through 0 dBs, as you see here. It passes from 0 dBs when omega is 1. So that is the second one. The third one has a one asymptote here. The second asymptote, again with a slope of -1 kind of. The fourth one is this one, slope of +1 now, as you see upwards. And the fifth one goes downwards, but it has a slope of -2 here. So each of these added up. You have to add these up, okay? Well, actually, you start from the lower frequency, lowest frequency. That is, you start from this 2 term, and to that one you add the first one. So your 1 and 2 added up will give you something, a straight line that goes like this. That will be, just go here, something like this. Okay, up to, let me just use another color here. It will be like this, up to here, and then this will go down a little bit more. Well, the slope is going, slope was -1, so the slope is going to be -2 up to where? Up to here, I suppose. And then the slope is going to be -1 again. And of course, this picture doesn't show it anymore. Let me copy it from the book and show it there. Okay, as I have said, you start with a straight line when omega is equal to 1. This is the addition, this straight line is the addition of, this is 14 dBs, okay? When omega is 1, this is 14 dBs. Then it has a slope of -1 or -20 dBs per decade. And then at omega equals 0.2, right? No, omega equals not 0.2. Omega equals 2. You have another line added up to it. So the slope becomes -1. And until 10. At 10, the slope becomes -1 or -20 dB per decade again. Until 50. Here, this is 50. Slope becomes -50. Sorry, becomes -60 because you have the quadratic term added up there. So this is the approximate curve. That is, these are the asymptotes, the straight line curve. Okay. And here you have 2. You have 1. These are the important ones: 1, 2, 10, and 50 frequencies. Now, you have to draw the exact curve. Well, these are in between. The only thing is that there is at the 50 frequency of 50 radians per second, I suppose, you have a resonance. And that resonance is, well, adds up, you know, the fifth one, the actual fifth one, if you look at it, it will be something like this. Let me go here. Something like this. And this one, the G of, let's say, J50 is going to be 1/2 zeta, the magnitude, of course, which is 1/2 times 0.3, so it's 0.6. And what is that? 1.3, something like that. And its logarithm will be what?
Hocam, I'm so sorry to disrupt. May you explain what is the usage of like approximate curve and exact curve? And what do we get from Octave if we like solve this question in the Are we going to have both the curves or just the exact curve?
No, well, if you want to, if I ask you something, it would be okay if you just give the approximate curve, okay? This will be 2.5 dBs actually, if I'm not wrong. So it goes up 2.5 dBs upwards from the approximate curve, although it doesn't look like it, it looks more. So there is a resonance there. Anyway, this is the exact curve. If you draw it, you are going to get something like this. The one that is on the this dashed line. Now, another thing is we have to look at the phases. This is the magnitude characteristics. For the first one, we have phase is 0. The second one, phase is minus 90 degrees. It goes from 0 to 90 degrees, sorry, 0 to minus 90 degrees. Omega equals minus 45. Not omega, phase phi equals 45 degrees at it is 0 to 90 degrees, phi equals 45 degrees at omega equals 10. And the fifth one is 0 to minus 180 degrees, phi equals minus 90 degrees at omega equals 50. So the phase characteristics, let me copy them for you from the book.
Hujam, what does the range of the angles represent? The 0 to minus 180 and 0 to 90. What does that represent?
Phase angle. What do you mean by that? Well,
but don't we have straight lines in the boat plot? So how does it have different range of angles?
Phase angles is not straight line.
So these angles, they're for the assumed plot that we made.
Excuse me.
With the asymptotes, the angles that we have here, the phase angles, they're for the asymptotic curves.
Phase angle. What do you mean by that? I didn't get what.
Like, Hojam, could you show in the graph where what these angles are for?
Well, these angles show the phase angles. What do you mean what they are for? No.
Have we represented these angles in a graph, or these are just that we know from the equations?
Well, we find them from the equations, yes, individual terms. We find the phases of the individual terms and then add them up.
Okay.
Okay.
Hocam, so
So-
this graph is the representation of the final form, right?
Well,
Not before adding it up. Because normally we draw straight lines for like 5 straight lines, one at 0, one at -90, one at 90, and one at...
well, here, what we did is the following. Let me explain that. Now, the first one, the first term is 0. It doesn't contribute to anything. The second one is this line. This is the second one. Okay. This line at -90. Okay. It's a constant, -90 here. The third one is 0 to -90 degrees with a with that, let me see. This is the third one. It goes like this. And what they did as an approximation is it's 45 at omega equals 2. Okay. So they just drew a straight line with 45 degrees here. 45 degrees at omega equals 2, as you see. This is the third one, this one. And then this one, 0 to 90 degrees, 45 degrees at omega equals 10. Okay. From 1 to here. So this is the fourth one. And the fifth one, it's complex poles. So this one starts from 0 degrees, goes to -180 degrees. Now this one is a little bit, it's not a straight line. It just they drew something like a tangent something. So the addition of 2, 3, 4, 5 all added is this curve. Okay. This is the approximate picture. Oh. Okay. So let me do this. Let's say. So let me just try to show it to you by using Octave. Okay. Yeah. So this is the numerator. The denominator is going to be, denominator will be the multiplication of it's called the convolution, but don't worry about it. 0.5 and 1. I'm just multiplying these things. I'm just adding an S to this.
Hocam tam olarak ne yaptınız com yazarak?
Yeah, okay.
Orada.
The conv is convolution. It just multiplies two polynomials. Okay. So it multiplies 0.5s plus 1 and s squared divided by 50 squared, 0.6 over 50 and 1. This conv operator multiplies two polynomials. Okay. I
Okay.
didn't want to do it by hand, so I just did it here. You understand?
Yes, thank you hocam.
So G is the transfer function of numerator and denominator. So this will be the system, I suppose. So we just plot the Bode plot of this C. I hope I did everything correctly. Yeah, I guess I did. Okay, as you see, this is the picture we get. We can paste it here. Not this one. This is what we have in the book. Where is that? Okay, if you look at it now, we see that at 10 to the 0, at one frequency 1, the gain is 50 dBs. And this phase starts from minus 90 degrees and goes to minus 270 degrees. And it is more or less this approximate phi of omega and the real phi of omega coincide more or less, as you see. There is this is 10 to the 1, 10, 20, 30, 40, 50. At 50, there is a slight increase, as you see in the magnitude. This is because of the small resonance there. And then it goes down with a slope of minus 60 dBs per decade. So this is the Bode diagram of this system. Well, this is kind of, it's not very easy to do by hand. And as you see, it's quite easy to do by a numerical software. So let me close this. Okay. Do you have any questions here? I know that this is not you are not very comfortable with all these things, okay? But you should know the basics up to a point. I understand that to get acquainted with this, you need a lot of practice and time. But I'm trying to show the very basics here. So, so we more or less have an idea about what the Bode plots do. They represent a system in the frequency domain, in the frequency response of a system. We will look at well, what is their use? We will just look at two important things. One is the how they are used in stability. And then we will look at how we can use them for specification of performance. That is how you specify performance of a control system in the frequency domain. We will try to look at those things. But before we go into stability, at this point, let's take a break because this will be a kind of a new topic. So let's stop here for a while and then we will go on, let's say 10 minutes later. Okay. Now, we have a feedback system. With a controller, C of S, and a plant, G of S, output Y, with a feedback. There might be a disturbance, but for stability, we are not concerned about that. Negative feedback and so on. Now we want to find a criterion for the stability of this system. Looking at the open loop transfer function. What is the open loop transfer function? By the way, let me just first let's remember the closed loop transfer function. Loop transfer function of this system was, as you remember, T of S, which was Y of S over R of S, okay? And this we defined as GC over 1 plus GC, as you remember. Now the open loop transfer function is, we define it as function, let's say, L of S, and you have seen this in steady state error. It is simply C times G of S. That is, C times G gives you the so-called open loop transfer. Controller times the plant. So that T of S is simply L of S divided by 1 plus L of S. Okay. We want to this is important to derive stability, let's say, of T of S, the closed loop system, using L of S only. Okay, we don't want to, go and find T of S, etc. We just want to use controller times the plant. And as you see in both the plots, controller times the plant is very easy because it's controller plus the plant. You just add up the logarithms of the frequency response. So if you have some criterion for looking at let's say, L of S, and derive stability of the closed loop system from there, that would be very useful. And that's what we are going to do. And that is, we are going to do by first looking at the following. We said that there are the Bode plots and there are the Nyquist plots. These are the complements of the Bode plots. The Nyquist plots basically plots the frequency response in one plot. It is the real part of the frequency response, real of G of J omega versus the imaginary part of G of J omega. It's not very important. The Nyquist plot is just a single plot of a system. We are not going to use it. I'm just going to show it to you, the real part. And this is the imaginary part, okay? And the Nyquist plot of a transfer function is simply a curve like this, okay? It starts at omega equals 0 and goes to here at omega equals infinity. And it's a curve. As omega increases, you get a curve that goes on like this. Okay. For different systems, you will have different Nyquist plots. Now, what is important for us is not the Nyquist plots, but rather the so-called Nyquist stability criterion. And I will give you this without a proof because its proof is rather involved. Okay. Now you have a system. As we have said, this is R. This is, let's say, this is L equals C times G. The open loop transfer function, this is Y. This is minus, this is plus. So the closed loop T of S is L over 1 plus L. L contains the controller and the plant, okay? The Nyquist stability criterion says the following. Plot the of L of j omega rather, okay? Which is L, as you remember, is C of j omega times G of j omega, okay? Open loop transfer function. It involves both the controller and the plant. So you plot it. This is the real, this is the imaginary axis, okay? And your plot is going to be, let me draw it in some other color. Something like this, okay? So start at omega equals 0, omega equals infinity, and it's here. Now there is a very critical point. This is this -1 point, okay? As I said, I'm going to give you this theorem without any proof. If L of j omega let's say plot of n circles -1 plus j0 point, then this is the Nyquist criterion. If the plot of the open loop transfer function encircles this -1 point, then your closed loop system is going to be unstable. For example, this plot I have drawn here is a stable one. But for example, this one, which encircles this -1 point, it gets it inside of its curve, and this one will be unstable. Okay. And this one, the red one, as you see, will be stable. The closed loop system is stable, not the L of j omega. The closed loop system made up of L over 1 plus L is going to be stable. And there is one condition here. G of S must be stable to begin with. This is a condition, okay, for this theorem to be correct in this form. That is the original plant of the system is going to be stable.
Hocam, the open loop transfer function and closed loop transfer function are equal in this topic, right? Because we don't have any feedback system. We have a unity feedback system.
No, they are not the same. No.
But we said G times C over
L,
1
open
plus.
loop transfer function is L. Okay. This is the open loop transfer function, and this is the closed loop transfer function. Unity feedback has nothing to do with it. Okay.
But I mean, we define L as G times C, and G times C over 1 plus G times C is the same definition we made to calculate closed loop transfer function. So aren't they the same thing?
Well, the closed loop transfer function is you know, C times G divided by 1 plus C times G, isn't it?
Yes. So L is the open loop transfer function only,
Yes,
right? Okay, okay.
L is the open loop transfer function.
Okay, okay, then. Thank you.
So we plot the real part of L versus the imaginary part of L, and that includes the controller inside it. L is C times G, does this. And then if it encircles this -1 point, your system is going to be unstable. Okay. For example, let's say that you have the following system. Let's say R, a simple one. The controller is simply a K. This is G. Okay. This is Y. So our L is K over S times S plus 1 squared. Okay, L of S. That's right, L of S. So if we plot the Nyquist plot of this, this is what we are going to get. This is the real part of L of J omega versus the imaginary part of L of J omega. This is this famous -1 point, let's say. The curves we are going to get will be as follows. This is one curve that is straight. As you increase your gain, you will be getting curves that are different. Now, if K is less than 2, this is K is equal to 2, and this is K is greater than 2. These are stable. This is unstable. If K is greater than 2, your system is unstable. And indeed, if I look at the closed loop transfer function here, T of S, which is L over 1 plus L, this will give me what? K over S cubed plus, what will that be? 2S squared plus S plus K, if I'm not wrong. S squared plus 2S plus 1 plus. Yes, this is correct. So this is the closed loop denominator, okay? And from the root criterion, actually, it is 1, 2, K, and the 2 minus K divided by 2, 0, and K. And we immediately see that K should be less between 0 and 2. 0 less than K less than 2 is the condition for stability. Okay. We see that if you plot the Nyquist plot, you see that your system becomes unstable in the limit of stability when K is equal to 2. And then if K is greater than 2, your system will indeed be unstable. Okay. Now, the same thing can be shown in the border, yes, in the border plot.
Hocam, can I ask a question?
Yes.
Hocam, this graph shows the pools of the L or zeros of the L. I didn't get it. Or it shows the T of L, transfer function of zero of transfer function or pools of the transfer function. What does this graph show, hocam?
This Nyquist plot, this plot, you mean?
Yes, hocam. Yes, hocam.
This shows, as I said, you have a, let's say, L of j omega. What is L of j omega? It is, let's say, k over, let's say, j omega times j omega plus 1 squared. Okay. This is a complex number, which is a function of frequency, right?
Yes, hocam.
We plot this complex number, its real part versus its imaginary part, increasing omega from 0 to omega equals infinity. We just increase omega and plot it. Okay? As I said, there is an important point which I'm not able to prove it because its proof is really takes a lot of time and it requires knowledge of theory of complex variables. If you encircle this -1 point with this plot, your system becomes unstable.
Hocam, what about which code should we write to get this graph, hocam, in the MATLAB or Octave?
In what?
Hocam, to get this graph, let's say, what should we write on the Octave or
You
MATLAB?
just write Nyquist.
Thank you, hocam.
But as I said, I'm not going to use Nyquist plots at all. I will just convert this now to border plots actually.
Hocam, I just had a question about at k equals 2, do we call it stable or unstable?
It's just in the limit of stability. You know, if you look at the time response at k equals 2, you will have sustained oscillations like a sinusoid. Just as
Okay,
we have in the
hocam.
DC motor case, for example. We are in the limit of stability. Okay?
Thank you, hocam.
Okay. So if you look at the border plot of the same system, this is the magnitude. This is the phase. We note something. What is the phase of this thing? Let me do it here. This point we said is important, -1. If you have a transfer function that passes through that point, let's say, exactly at that point, what is the magnitude and phase of this transfer function at that point, okay? Let's say this is the real and this is the imaginary axis. This transfer function at this point has a magnitude is equal to what? What will be its magnitude? 1, isn't it? It will be a, it will be a vector of this size. Its magnitude will be 1. And what about its phase? It's here. 180 degrees, or minus 180 degrees, which is the same thing actually. So do you see that? Any response? Is this clear or unclear? Should I repeat?
Hocam, may you
Hocam,
repeat it?
can you please repeat?
Okay. Well, we are looking at a transfer, this is just complex variables. You have a point, -1 point, okay? And you have a transfer function. You have a curve that passes through that point. This is a, it's like a g of j omega curve. This can be written as, g of j omega can be written as its magnitude and its times, let's say e to the j, let's say 5 of omega. Okay. This is the magnitude, this is the phase. This is the polar representation. Okay. So at omega equals, let's say, no, not omega. When g of j omega is exactly equal to -1 plus j0, if it somehow is exactly equal to that, what is the magnitude and what is the phase of the transfer function? What is the magnitude? Magnitude is it is 1, and its phase phi is equal to -1. -1 is, this is the real part. This is the imaginary part. It has an angle of 180 or -180 degrees. Okay. Do we agree?
Yes,
I
Hocam.
think it's pretty clear, but
Yes,
so at the limit of stability, when the phase angle is let's say -180 degrees, the gain of your system will be 1, or in terms of decibels, it will be 0 degrees. Okay. So if I plot this, well, let's say that I take this this example, L of S equals K over S times S plus 1 squared, and K is equal to 2 is the limit of stability, we know that. So I plot it at K equals 2. So what I get will be something like this, if I'm not wrong. Let's say this is 0.1, this is 1, this is 10, etc. It will be some plot like this. Doesn't matter, the exact shape doesn't matter here. Whereas the phase angle starts from, let's say, -90 degrees, this is -180 degrees, and this is 170 degrees. something like this. Okay. But the important thing is actually exactly at omega equals 1 for some reason, omega equals 1, this value is 0 dBs, and this value is 180 degrees. We are at the limit of stability, and here you have k is equal to 2. Well, if you have increased the gain a little bit, or let's say we increase it not a little bit, but a lot. Let's say that I plot k is equal to 10 here. It will be a line that is parallel to this one. This is k equals 10. If I increase the gain, actually nothing will change in the phase plot. The phase plot will be here. But when this thing cuts this 0 dB or one line, if I go here, my phase angle is going to be this much. If I go here, this will be our phase angle when k is equal to 10. So the phase angle is going to be something greater than minus 180 degrees. And let me use another color. But if I use a smaller k, let's say k is equal to, well, I don't know, 0.5 or something. The phase is going to be the same, but if I go here, the phase here is going to be less than minus 180 degrees, as you see. Or should I say greater than? Yeah. Anyway, it's above 180 degrees. So as we see, and as we know, this thing is stable, whereas this yellow one, the green one, is unstable. Okay, the phase is greater than 180 degrees, whereas the phase here is less than 180 degrees. What happens is in this picture is the following. Let's see. At some point, as you see in these transfer functions, you have, oh, sorry. This distance is 1. And here you have, let's say it's 1, although it doesn't look like it. Okay. As you see, the one that doesn't encircle minus 1 point has the transfer function is equal to 1 when the phase is below minus 180 degrees. Whereas for the unstable one, it has a phase of when the magnitude is 1, the phase is above 180 degrees. So we see that in the border plot, this is the typical picture we get. So in most systems, the system becomes unstable as the gain is increased above a certain point. So for this system, we see that, for example, for k is equal to 2, you are in the limit of stability. If you increase it a little bit further, your gain and phase characteristics show whether your system is stable or not. Actually, this just shows that this is important. When L of S or L of j omega, I should say, equals or exactly is equal to 1 or let's say 0 dBs, okay? If is less than means what? Like more, this is more than minus 100. Conversely, this is one thing. Another thing is when phi of omega, which is the angle of L of j omega equals 180 degrees. If the when I say the system, I should say, okay, let me just, what do I mean by the system thing? The system thing, which I put inside this, is equal to, I mean the following, the closed loop system. Okay. Well, just looking at the properties of L of S, we try to find the properties of the closed loop system. Okay. This is obviously at first sight, when you first encounter this looks very, very complicated. I am sure it is. But this is, I don't know how to make it any simpler than this, actually. I try to make it rather look easy. I try to, okay? So when you look at, when the phase is 180 degrees, you go up for the second criterion. When the gain is below 0 dBs, your system is stable. When your gain is above 0 degrees, 0 dBs, it is your system, your closed loop system is going to be unstable. Okay, that's what this thing, this Nyquist theorem implicates. What its implications are. So in most systems, therefore, we have we have the following property. The system, let me call it the system, means the closed loop system. Actually, it can be plus minus 100. So, as a measure of stability, we define the following measure of relative stability. We define the following quantities: gain and phase margins. Okay. We basically know that as you as L of j omega gets closer to, let's say, -1 plus j0 point in the Nyquist plot, the closed loop system becomes closer to instability. As we have said, so let's say that this is the -1 point. This system is more stable than this one, for example, although both systems are stable, as we know, because they don't encircle this -1 point. But the first one has better stability than the second one, okay? Because it's far away from this -1 point, okay? This is real, this is imaginary. Better, let's say, in terms of stability. So we want to have the closeness of this your open loop transfer function to -1 point. We use it as a measure of relative stability. So let's say we use closeness of L of j omega to -1 plus j0 point as a measure of, let's say, relative stability. And we define it as such. We define it as follows. Let me just draw it here. This is the real of L. This is the imaginary of L. And let's plot this something like this. And let's have that this infamous -1 point here. Okay. Now this -1 point, we can draw a circle around it like this. So this circle has a radius of 1, as we see. Okay. We define, for example, the phase angle when your transfer function crosses this -1. The difference between the phase and this thing, this angle, and the phase of 100, this -1 point has a phase of -180 degrees, and this is the actual phase. This thing is called the PM, and PM is called the phase margin. the larger this phase margin is, the better for you, okay? Because you are far away from getting close to this -1 point. The secondly, this distance now, when you cross this -8 point here, when you cross the real axis, this distance is defined as 1 over the gain margin. And Gn is called the margin of your system. So when 1 over the gain margin is, for example, when the gain margin is, let's say 2, your gain is 0.5, for example. Okay, so you are far away from -1. When your gain margin is, what is that? When you are here, your gain margin will be, well, 1 over 1, it will be 1. But in terms of decibels, it will be 0 dBs, for example. Let me define the following phase margin. So, gain margin and phase margin are closeness of measures of closeness of this your transfer function to the critical point. In terms of Bode plot, let me show this also. for example, again, I will use this example, g of s, sorry, L of s rather. L of s equals k over s times s plus 1 squared. And I will take k to be 1 so that it is stable. Okay. These are omegas. It just shows like this for some reason. This is the phase. It's 90. So the phase looks like something like this. And the gain looks like something like that, I suppose. Anyway, so what we get here is when the phase is 180 degrees, we go up, and what we see here is 1 over the gain margin, which is equal to mm, 0.5, from which we get that gain margin is equal to 2 here, okay? Or you can take the logarithm of that to find it in decibels. And the phase margin, when you look at the gain, what is that here? You go there when the gain crosses this one, you go here, and this distance will be the phase margin, which is like 2 degrees or something like this. So I know that this is not very clear at this instant. I'll try to do a few more examples. Maybe I'll give you more examples in a solved manner. But these things are indicate relative stability, and they are used as design criteria. Okay, GM and PM are used as design criteria. That is, you try to achieve certain aims with the gain and phase margins. For example, there are these ASME rules actually for gain and phase margins. Let me see where I put them. Messed up here. I think the phase margin should be greater than 30 degrees, and the gain margin should be greater than 2. And 2 GM greater than 2 means GM is greater than 6 dBs, I think. Okay, they are the same thing if you take the logarithm. So if you try to design a control system, you should try to achieve these phase margin and gain margin criteria in your control design. Okay, these are the relative stability indicators which are necessary in the design of the control system. As I said, they are at this point they look very abstract and you don't know what to make of it. But as you work on these things, they will have more meaning if you work on these things. Okay, these are the rules, for example, empirical rules, just as you have in the tuning of Ziegler-Nichols design, tuning of PID controllers. You try to keep the gain and phase margins at a certain level, for example, in your design. You select the control gains so that your system satisfies these criteria. I'll try to give a few more examples the next time. And we have only 1 hour left, I know, but I'll try to explain it better. Okay, that's all for today. If you don't have anything else to say. Any
Hocam,
questions? Yes.
if nobody has a question, I have a personal question to you. Anybody has a question?
What do you mean personal?
Lab report related question about
Okay,
other.
we can talk about that later. Okay.
Okay.
After the lecture.
Yes. Okay.
Hocam ben midterm'den bir şeyler sormak istiyordum ama vaktiniz varsa.
Kim? Emre sen misin?
Evet hocam benim.